This video will focus on some basic concepts related to chemistry. Hopefully this is review for you if perhaps you have had chemistry in high school. But the reality is it's almost impossible to separate biology from chemistry. So therefore, an understanding of basic chemical concepts is really crucial to understanding basic biology. So some of the topics we'll focus on listed on the screen there for you. Let's begin by just taking a brief look at the periodic table of the elements. I'm sure you have seen this sort of thing before. Let's focus for a few minutes just on some of the elements. For example, we see helium, carbon, nitrogen, oxygen. Right? These are things, of course, you have heard of before. Notice that within each box, not only is there an abbreviation for each element, helium, for example, there's also a number up top and a number down below. The top number, that represents the atomic number for each element, and that represents simply the number of protons found within each element. And that's pretty crucial because that's what distinguishes one element from the next. Also within each box, the lower number here, so for helium, for example, there's a number 4 or 4.0026. That's the atomic mass. So that essentially represents the number of protons plus the number of neutrons. If we look at this basic information that we see in the periodic table, we can use that to sort of reconstruct or illustrate the basic structure of an atom. So let me just backtrack. I guess hydrogen is not listed here, but hydrogen has an atomic number of 1. Carbon, an atomic number of 6. So again, hydrogen 1 proton, carbon 6 protons. Let's use that information to illustrate what atoms might look like. So for example, here's hydrogen on the left, atomic number of 1, so 1 proton, balanced by 1 electron. Notice there are no neutrons here, and that's kind of unique. Most elements do have neutrons, but hydrogen doesn't. Carbon, recall we said carbon has an atomic number of 6. So 6 protons in the nucleus, 6 neutrons as well. And then if this is a balanced atom of carbon, we'll have to accommodate 6 electrons. Notice this first electron shell contains 2. In fact, this first electron shell can only hold 2. So there are 2 of the 6 electrons illustrated here. The remaining electrons are found in an outer shell of electrons, which contain 1, 2, 3, 4. This outer shell can hold up to 8. But of course, carbon only has 4, since we've already accommodated for the total of 6 electrons in carbon. So this outermost shell, again, you perhaps have heard of the octet rule, except for the first inner shell, which can only hold up to 2, all subsequent shells can hold up to 8 electrons. And this is pretty crucial. The outermost shell of an atom, we also refer to it as the valence shell. And this is where a lot of the reactions take place, and it also determines how many bonds an atom can form with other atoms. So to illustrate that basic concept, let's just take a look at hydrogen. Again, we said this first shell of electrons is able to hold up to 2, but yet a single hydrogen atom just has 1. So what happens is 2 hydrogen atoms come together and they essentially share their electrons, and therefore they're sort of satisfied, if you want to think of it that way. And this is a simple example of a covalent bond, right? The characteristic feature of covalent bonds is, again, this sharing of electrons. Pretty strong bonds, very, very important in biologically important molecules. So instead of just having single hydrogens, we typically have H2, or hydrogen gas. Okay, so again, covalent bonds characterized by this sharing of electrons. Carbon, although we're not going to illustrate it per se, but carbon, notice it has 4 electrons in its valence shell. And recall we said this shell can hold up to 8. So therefore, carbon quite often forms covalent bonds with 4 other atoms. Again, that's crucial, as we'll see later, in the construction of biologically important molecules. In addition to covalent bonds, another pretty relevant bond are these ionic bonds. Ionic bonds are illustrated here using sodium chloride or table salt as kind of a classic example. So sodium has an atomic number of 11. So sodium illustrated up toward the top here. So atomic number of 11, so 11 protons in the nucleus. How about the 11 electrons? How are they configured? Well, again, the first shell can hold up to 2. The next shell can hold up to 8, so now that's 10. So there's one additional electron in this outermost or valence shell. It doesn't take much for that electron to be lost. If the sodium loses an electron, overall it becomes positively charged. So we say it has formed an ion. Likewise, if you take a look at chlorine, illustrated toward the bottom here, chlorine has an atomic number of 17. So how are the electrons configured? Well, again, 2 in the first shell, 8 in the next shell. That's a total of 10. So the additional 7 electrons, 2, 4, 6, 7, found in the outermost shell, it would be satisfied if this chlorine could actually gain an electron. And so it can do just that. If it picks up an electron, let's say lost from sodium, chlorine now becomes negatively charged. And what happens when you have two things with opposite charges? Well, they're attracted toward each other. So the sodium ions and the chloride ions, they are attracted to each other by these ionic bonds. Not a super strong bond, but strong enough to hold these ions together, for example, in the form of table salt. But weak enough so that when you take salt and dissolve it in water, those ionic bonds can be broken fairly easily. And as we'll see later, when we look at structure of proteins and DNA, ionic bonds play an important role in the configuration of those molecules. Now let's take just a minute and look at the structure of water molecules. Water obviously profoundly important for life as we know it. So a little more detail than you need to know in this image here, but illustrating the structure of water, H2O. So 2 hydrogens, illustrated by these blue spheres here, and oxygen, illustrated by the red sphere here. What can we say about the structure of water molecules? Well, it turns out that oxygen is electronegative, meaning that oxygen has a tendency to hold on to electrons more strongly than do the hydrogens. So these 2 hydrogens, again shown in blue, are bonded to the oxygen through covalent bonds. So they're sharing electrons, but again, oxygen tends to hold on to those electrons more strongly than do the hydrogens. So what then are the implications? Well, it turns out that as a result of this unequal sharing of electrons, the oxygen tends to have a slight negative charge, whereas the hydrogens have a slight positive charge. So let's illustrate that in just a moment. So if we sketch out a water molecule, again very schematically here, so H2O, so 2 hydrogens. Again, these lines that you see there between the hydrogens and the oxygen, what kind of bonds are they? Well, they just represent covalent bonds. So again, if the oxygen holds on to the electrons more strongly than do the hydrogens, we'll do this. There's a slight negative charge on the oxygen, slight positive charge on the hydrogens. So what's going to happen when you have water molecules adjacent to each other? As you can imagine, and again I'll put these slight charges here as well, you can imagine that the oxygen in one water molecule will be attracted to hydrogens of an adjacent water molecule. Right? So this attraction here, this is what's referred to as a hydrogen bond. Okay, so hydrogen bonds, fairly weak, but as we'll see later, profoundly important in many types of biological molecules. So hydrogen bonds, very important. I mean, we just used water as just to illustrate hydrogen bonds, but important in other molecules as well. It's because of this hydrogen bonding in water that really imparts lots of important properties to water. I mean, just a few examples. We see things like cohesion, where water molecules are sticking together. Capillary action, very important in helping fluids move through different parts of organisms. Many other features of water do impart to hydrogen bonds as well. The final concept that we'll focus on here is that of pH. So you've heard of acids and bases, very, very crucial to life as we know it. pH is really nothing more than a way to illustrate the concentration of protons in solution. You've heard of the pH scale. You've seen things like things being neutral or acidic or basic or alkaline. And what do these refer to? So we say, for example, something with a pH of 7, that's neutral. Well, what does the number 7 actually refer to? That's just the concentration of protons in solution. So something with a pH of 7, so if you took pure distilled water at room temperature and standard conditions, the concentration of protons would be 0.000006 molar, or an easier way to illustrate that is 10 to the negative 7th. The negative 7, that's where we get this 7 from here. So the pH number is just the negative concentration, the negative logarithm of the concentration of protons in solution. Okay, so, and again, anything below 7 we say is acidic, anything above 7 is alkaline or basic. What are acids? Well, acids are anything that tend to increase the concentration of protons. Bases are anything that tend to decrease the concentration of protons. So just keep in mind, and often a source of confusion for many people, is that acids, the lower the pH number, the more acidic something is, and the higher the concentration of protons. Something that's alkaline, they have a higher pH number, and they actually have a lower concentration of protons. Why do we care about pH? Why do we mention here? Well, it turns out that pH is very, very important. In fact, within your body, there are lots of systems in place that keep the pH of your blood right at a very specific pH. If it goes too much above or too far below about 7.4, that could mean death to the organism. So why do we care about pH? Well, shifts in pH, if it's too acidic or too alkaline, can disrupt the structure and function of proteins. That can have drastic consequences. This can also tend to shut down chemical reactions, again, if the pH goes too far to one extreme or another. And also, cell membranes are pretty sensitive to fluctuations in pH. So again, anytime you have a solution, anytime you have a water-based system, it's going to have some concentration of protons, and the concentration of those protons is really crucial to proper functioning of living organisms.